Okay, welcome to lecture here. We're going to wrap up chapter, excuse me, we're going to wrap up chapter 3, and we're going to actually roll into chapter 5 after that in case you need the notes. We'll talk about some other things here. Okay, so we've been talking about chapter 3. We're talking about geometry and Lewis structures. And again, here, we're going to wrap up kind of where we left off. We were in the middle of sort of the geometry. We were talking about really two types of names. One's electron pair geometry, which sort of describes the electrons around the central atom. And one is the molecular geometry, or the shape, which is the overall shape of it. For our purposes here in lecture, as I mentioned last time, we're just going to focus in on the molecular geometry. Again, that lab that you did last week, I think, dealt with the electron pair geometry as well. So we're just going to do with the molecular geometry here. When we do geometry, we can base it off of our Lewis structures that we draw. And a couple of important things when we do it, and really one sort of important thing, if you will, in terms of determining the geometry of a molecule. It really is, especially when you have more than two atoms. If you just have two atoms in a molecule, a diatomic molecule, geometry is pretty easy. It's always going to be linear. So there's just two atoms, so it's going to be a straight line. So it will always be linear. Then when we do get three or more atoms and we're doing geometry, it is always the central atom, which is the important one. And when you go to the central atom and you're doing that type of geometry, the important part is to look at the central atom and figure out how many electron pairs does it have and how many bonds does it have. And when you're counting electron pairs and you're counting bonds, the important thing is if you draw something that has a double bond or a triple bond, it counts as only one electron pair and also one bond. So that's really important when you're doing that type of geometry. So it does have more than those type of bonds, but in terms of just the geometry part, if it's a double bond or a triple bond, one electron pair and one bond in terms of counting them. So where we left off was right here, which I think is ammonia, NH3. And if we draw NH3, it looks something like this. And if we look at it, again, always the important one in terms of geometry is that central atom. And if we go right here, our central atom has one electron bond, two electron bonds, three electron bonds, and four electron bonds. Not electron bonds, sorry, electron pairs. Four electron pairs. In terms of bonds, it only has one bond, two bonds, and three bonds. So four electron pairs and three bonds. And if you remember, when we talk about the electron pair geometry, it is based just on the number of electron pairs. They could be dots, they could be lines. So in this case, something with four electron pairs will have the geometry known as tetrahedral. But as we started talking about at the end, it also has our non-bonding electrons. It has our bonding electrons near each other. So we get a lot of different types of electrons interacting with each other. So because of those non-bonding electrons being present, it will cause the overall molecule basically to kind of spread out a little bit more than it can. And it ends up getting a molecular geometry as being trigonal pyramid. So this sort of non-bonding electron sort of comes up like so, makes kind of like a triangle shape, and then on the bottom also makes more of a pyramid type shape. Again, trigonal pyramid would be the molecular geometry that's going on with four electron pairs around the central atom and three bonds. So a couple of things about trigonal pyramid, which is very commonly sort of messed up on, is trigonal planar that we saw earlier. Trigonal planar is three electron pairs and 3 bonds. And that's that more triangle type arrangement. And trigonal pyramid, which is what this guy is, they are 2 different things. So on an exam, quiz, something like that, if you just write trigonal, that is not the right answer. You do need to commit to either trigonal pyramid or trigonal planar, as they are both different things here. So you want to make sure that you write the whole thing. Don't let me choose because I will make it wrong. Yes, so make sure you either put planar or pyramid. They are 2 different things. Again, trigonal planars that we saw earlier is not the same thing as trigonal pyramids, so they are different. So make sure that you really do choose the right one when you go to write it there. In terms of the bond angle here, it'll be a little bit less than our traditional bond angle of tetrahedral, so a little bit less than 109.5 bond angles based off of the electron pair geometry sort of thing. And our last geometry here is something like water here. And if we look at water, we have 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs there. And something with 4 electron pairs also has 1 bond and 2 bonds. So with 4 electron pairs, again, in terms of the electron pair geometry, it is going to be tetrahedral. Because it does have the 4 electron pairs. But the molecular geometry will be a little bit different, or the shape of it. And that is because this has all the kind of really bad interactions that can happen. We have non-bonding electrons near bonding, we have bonding electrons near bonding electrons, and we have non-bonding electrons near non-bonding electrons. And these non-bonding electrons definitely do not want to be near each other, so they move as far away as they can. And as a result, our bonding guys also move, and we end up with a shape that's known as bent or V-shaped. And it also has a bond angle of less than 109.5, something like 104 in this particular case, Celsius. This is about 104. The NH3 was about 107, and our CH4, which was straight tetrahedral, has 109.5. So it is slightly different. And again, it's because of these non-bonding electrons. There's nothing bonded there, has a little bit more room for movement, and as it moves, it really kind of makes the overall shape of the molecule change along with it. So any questions on that there? Okay. So here's a table from your book about what we were talked about. So these are the geometries that you need to know. And again, like I mentioned before, you do need to know really just the molecular geometry or the shape of it. You don't have to worry about the electron pair geometry. So this is essentially what we talk about: 2 electron pairs, 2 bonds, linear, 3 electron pairs, 3 bonds, trigonal planar, 4 electron pairs, 4 bonds, tetrahedral, 4 electron pairs, 3 bonds, trigonal pyramid, and 4 electron pairs, 2 bonds, bent or V-shaped. And we had 3 electron pairs and 2 bonds, which was our angular one, which is not on here. And again, so really this is the easiest way to sort of do geometry, is really just to memorize. And again, this is basically number of electron pairs around the central atom, and this is essentially the number of bonds. And that's sort of the best way to really sort of figure out what's going on, is to just draw your Lewis structure correctly, always the central atom, and count it around. Any questions on geometry or anything like that there? Okay. You do not have to worry about bond angles either for us, so it's okay. So you don't have to worry about bond angles or electron pair geometry. So again, just the molecular geometry you do need to know. Okay. So last thing we're going to talk about in terms of bonding is polarity of molecules. And when we're talking about the polarity of molecules here, we're actually talking about the overall polarity of the molecule. Either the molecule will be polar or nonpolar. And if you remember, we talked about individual, what is sometimes referred to as bond polarity. And that is when we use that electronegativity values. So that differences in electronegativity values we were able to draw an arrow pointing to the more electronegative, and the one that makes like the plus sign, the least electronegative on the other side of it. And here what we're looking at when we talk about the overall molecular polarity is the entire molecule as a whole. So the entire molecule as a whole, is that molecule polar or nonpolar? Kind of means the same thing in terms of what we're talking about here. What it means is if we have a polar molecule, overall what that means is there's a part of that molecule that is more positive, and there's a part that's more negative as an overall unequal sharing of electrons in the entire molecule. So if we have a nonpolar molecule, what that means is overall what we have is essentially equal sharing of electrons distributed equally among the entire molecule. There's not a part of the molecule that is more positive. There's not a part that's more negative. It is just kind of equally distributed, all those electrons. Almost neutral, you could kind of think of it. It has no charge. It's sort of a neutral molecule. So let's take a look at a couple of examples here as to what we're talking about. Let's talk about really the easiest ones to determine, and those are diatomic molecules. So diatomic molecules are guys that only have 2 atoms, and they really are the easiest ones to determine whether or not something is polar or nonpolar. So for example, if we look at a couple that we've seen before, like F2, and when we look at F2 in terms of electronegativity, if we take the differences in electronegativity here, that is going to give us a difference of 0. And that tells us that this bond right here is a nonpolar bond. Now, because this is a diatomic molecule, this bond right here that we just identified as being nonpolar is the only bond there is in the entire molecule, which means by default, this entire molecule should be a nonpolar molecule. Same thing if you did H2. Again, this bond right here would give you a difference in electronegativity of 0, and this is a nonpolar bond. And because this is the only bond there, the molecule itself also has to be nonpolar. And what that means is we would expect equal sharing as a whole across this whole entire molecule. Again, there's no side that's more positive or negative because of unequal distribution of electrons. Now, if you have a different guys bonded together, so if you got something like HF, which we also saw, I think, earlier, what we know in terms of HF, this is like 2.1. This is an electronegativity value of 4. Difference in electronegativity value is about 1.9 when you subtract that. That means that fluorine is more negative, so we could draw that dipole arrow pointing towards the fluorine. That means that the fluorine is more negative, the hydrogen is more positive. So in this particular case, it contains a polar bond. And the same reasoning here, this is the only bond in this entire molecule, which means that this molecule would be a polar molecule. So diatomic molecules are really super easy to determine if they are polar or not, or nonpolar. And it's basically looking at the bond. So if the bond is polar bond, the molecule will be polar. If the bond is nonpolar, then the molecule will be nonpolar. And again, that's because there is only one bond in the entire thing. So if that bond is polar or nonpolar, it means the whole thing is going to be that. Now, that would be great if everything was that super easy, but it's really not. So when we get to molecules that have 3 or more atoms, you have to look at a couple of things. First off, you have to determine, is there polar bonds? And if there are polar bonds, you have to look at the molecular geometry to help you decide whether or not the entire molecule is polar or not. So let's take a look at an example here. Let's say we looked at CO2. And if we draw CO2 like so, I won't put the dots in on the oxygen, but if we draw CO2, it does look something like this. Now, when we're looking between carbon and oxygen, we want to know if that bond is polar or not. And you could look at the periodic table. If you look at the periodic table, you will see this arrangement here: carbon, nitrogen, oxygen, fluorine. Carbon is further to the left than fluorine. and oxygen, and that means that oxygen is going to be more electronegative than carbon. And if we were to draw bonds, they do have polar bonds. One would be heading towards the oxygen this way, and one would be heading towards the oxygen in this case. So this is like number one question is there polar bonds? The answer is yes, there are polar bonds here. So you may think to yourself, there are polar bonds. This thing definitely has to be a polar molecule. It kind of makes sense. It's got polar bonds, should be a polar molecule. But what you do have to look at is the geometry here. And this guy is, if we do the geometry, 1 electron pair there and 2 electron pairs there. It also has technically 1 bond here, even though it's double. Remember, it counts as 1, and 2 bonds here. So it has 2 bonds and 2 electron pairs. The geometry of this guy is linear, which means basically it's a straight line. And because of the geometry of this molecule, this guy is actually going to be nonpolar molecule. And that is because if I take like my pen here, or a pen, and basically if this is my CO2 molecule, if I pull this way where an oxygen is pulling, and then I have the oxygen pulling the other way, if you look at my pin, I really am pulling on both sides, and my pin is really not going anywhere. And what happens in this case is, even though it has polar bonds, because of the geometry of it, it is actually going to cancel each other out. So these bond dipoles cancel each other out, and we end up getting a molecule that is going to be nonpolar. And this is a very good example to show that you can definitely have a guy that has polar bonds, but because of the geometry, they will cancel out. And that is because these individual bond dipoles, which we draw with the little arrow here, these are what are known as vectors. And I vaguely remember physics, but vectors have direction and magnitude, and then I fell asleep and don't remember the rest of it. But I also woke up long enough to remember that in certain cases, vectors will cancel each other out, and in certain cases, vectors will add to each other. In the cases where they cancel each other out is whenever they're kind of going in equal and opposite directions, or they're like heading right at each other. Cases where they add to each other is when they're not doing that, basically. So these guys will cancel, and CO2 is going to be nonpolar because of that. If we look at another example like water, and if we draw water here, again, looking at the individual bonds in water, the hydrogen and the oxygen, it is going to be a polar bond, and the oxygen is going to be more electronegative than the hydrogen. So if we were to look at the electronegativity values and draw our arrows, they should point to the oxygen, which is more electronegative. So yes, this also has some polar bonds. We also want to look at the geometry, and as we saw earlier, it has 4 electron pairs and 2 bonds, which means the geometry here is bent or V-shaped. And what's going to happen in this case is, even though these guys may appear to be heading at each other, they're actually going to add together in this case. And what's going to happen is you're going to get what is sometimes referred to as a net dipole moment, also represented by this arrow, heading in this direction. And basically what that means is the oxygen is going to be more negative. So the oxygen side of water is more negative. The hydrogen side of water is more positive. Again, in terms of the vectors, how it works something like this. You draw one vector heading in the direction it was heading. You line up the other vector at the arrow of it. And what they will end up doing in this case is actually adding to each other in that direction. And it actually will give you a more negative side on oxygen and a more positive side on hydrogen. And that means that this guy is going to be a polar molecule. So when you're looking at polarity, again, molecular polarity, especially when you have 3 or more atoms, you do want to make sure that you look at both, is there polar bonds, and is there the geometry, is it? Yeah, so I think I'll answer your question by what I'm going to talk about next. So if I don't, let me know. But I think to answer your question, and just in general, sometimes it's really hard polarity for people to sort of figure it out. And sometimes people really don't want to kind of draw vectors and all that kind of stuff. So, there's a pretty safe sort of way that you could kind of determine probably relatively quickly whether or not a molecule is polar or non-polar. Probably not 100% all the time, but 98, 97, pretty good high up there. And you can look at the geometries that you have. And there are certain geometries which are referred to as being symmetrical geometries. And symmetrical geometry are geometries, i.e. symmetrical geometries are ones that we've seen in this class, which are trigonal, planar, and we're talking about the molecular geometries here. So molecular shapes, molecular geometry, and tetrahedral. And what both of these guys have in common is if you draw the Lewis structure, there are no non-bonding electrons on the central atom. So if you draw your Lewis structure, you got no dots on the central atom. And the other thing, everything attached is the same. Everything on the outside atoms are the same. It's a pretty good chance that this molecule will end up being nonpolar because everything is symmetrically opposites of each other. Now, if you take something, for example, like CF4, again, I'm not going to draw all the dots on the outside, but if we look at the central atom here, after we do all the dots technically on the outside, there are no dots on the central atom. Everything on the outside here is exactly the same. It's tetrahedral in terms of geometry. They're all going to cancel each other out because they're basically going to be all heading towards the fluorines. You draw those arrows, they're all going to go towards the fluorine, which is more electronegative. And they're going to pretty much cancel each other out. And this is going to give you a nonpolar molecule. Now, if you take, go back this way, let me borrow this page here. If you take that exact same thing and you take all of those fluorines, but you take off one of the fluorines and you substitute it in for like a hydrogen, for example. Now what you have is everybody pulling towards the fluorines. And now instead of this guy pulling the opposite way on the hydrogen side, you have really a nonpolar bond here. So what you essentially have is all three of these guys pulling this way, this guy not really doing much. And what will happen in this situation is this will then go from being a nonpolar molecule like it was in the previous example to becoming polar molecule. So symmetrical geometries where basically you have trigonal, planar, or tetrahedral, you pretty much draw your Lewis structure, no dots on the center atom. Everybody on the outside atoms are exactly the same. Pretty safe bet to go nonpolar molecule. If you take one of those atoms on the outside in that situation and change it to a different element, it's a good chance it's going to become a polar molecule. Any questions on that way? Now that leaves us the unsymmetrical geometries. And unsymmetrical geometries will be your angular, your trigonal pyramid, and your bent or V-shaped. And what all these guys share in common is if you draw the Lewis structure, you're going to see non-bonding electrons on the center atom. So non-bonding electrons on the central atom, Ca. Basically, you draw your Lewis structure, you see dots on the central atom. And if you see dots on the central atom and everything on the outside is the same, in terms of the element, it will most likely be a polar molecule. So, for example, NH3, we draw it. What I'm really looking for is I see dots on my central atom. I see everybody on the outside is the same. This is going to be a polar molecule. the example we had earlier, which was water. I see dots on the central atom. I see everything the same on the outside, also going to be a polar molecule. So that's really sort of the easiest way to sort of figure it out is dots on the central atom, everything the same, polar. No dots on your central atom, everything the same on the outside, going to probably be nonpolar. If you change that no dots and put something else on the outside, it becomes a polar molecule. So that's sort of the easiest way to sort of figure out molecular polarities, to do it by sort of the symmetrical geometries, unsymmetrical geometries. Lastly here, linear geometry is really the only one you have to think about. So like in CO2, where those guys were heading in the opposite directions, they cancel out. You could have a situation in a linear arrangement where everybody is heading in the same direction, and it would be a polar molecule. So linear is really the only one you have to think out, but it is kind of like a straight line. So it's pretty easy. You could think about polarity as like tug of war. So if people pull on the rope equal and opposite, the little arrow thing is not going to go anywhere, and it'll be nonpolar. If somebody's able to pull more in a linear situation, one side or the other, it will become a polar molecule. Questions on that there? So here are some examples. I think that was, there you go. Yeah. So really in terms of geometry, I think that's sort of the easiest way to do it. There you go, that one there. All right, let's take a look at some examples to see how this sort of works here. So what we're looking at here, in this particular case, we got trigonal planar, so no dots, but here we do not have the same things attached. So this is going to become a polar molecule in this case. The carbon-oxygen bond is polar, and because of that sort of geometry, we do not see it. Here we have no dots on the central atom. Everybody is the same. Again, this is our triangle geometry. It's going to be nonpolar. This was the NH3 we did earlier. Everything's the same on the outside, and I see dots on the central atom, going to be a polar molecule. Here, no dots on the central atom, but we're not all the same on the outside, going to be polar in this particular case. So again, this is the way you could kind of look at it really quick. So let's think about some of the ones we did or seen before. So let's do this one. Let's see, let's do this one here. Let's do this one, and let's do this one here. Okay, take a second or two and figure out, are these guys going to be polar or nonpolar? Just based on geometry, nothing else. So just based on geometry, will these guys be polar or nonpolar? Okay, let's take a look at it. And again, I'm just going to kind of do it like we've been talking about. And again, like I said, it might not be 100% foolproof, but pretty close, I would think. So really, here's how I would do it. I'm going to look at the central atom. I see dots. I see things that are exactly the same on the outside. I'm going to go polar molecule. Same thing here. I'm going to look at the central atom. I see dots on my Lewis structure. I think everything's the same. I'm going to go polar molecule. Here, there is no central atom, but this is diatomic molecule, which means they are both the same. There's only really one bond here, which is this triple bond in between them. And since they are both the same, this bond here would be a nonpolar bond. And because it's the only bond in this entire molecule, this would also be a nonpolar molecule. And lastly, what I would do here is look at the central atom and go, I see no dots. I see everything that's on the outside is the same. And I would go nonpolar on this guy as well. And again, based on geometry, I would go nonpolar. Some people might say, hey, it has a charge, so it's polar. But just based straight on geometry, this is still a trigonal planar type triangle. Everybody's going to be pulling equally to each other. And it probably should be best classified as being nonpolar. Questions on how to do polarity? I would probably keep it that simple for our purposes here. Again, basically dots or no dots on the central atom. And again, if everything on the outside is the same with no dots, going to be nonpolar. Everything on the outside is the same with dots, probably going to be a polar molecule. And again, the only thing you have to worry about is if you have no dots in, like the one we saw earlier, you know, if something gets switched out and they're not all the same, then it's going to go from being nonpolar to a polar molecule. So that's probably the best way to do it. Any questions on molecular polarity? Okay, so that should wrap up chapter 3, which obviously is on the exam, which is a week from Wednesday, not this Wednesday, but a week from Wednesday, we're going to take it. And it will be on chapters 1, 2, 3, and 4. Any questions on that? So let me tell you about chapter 4. So chapter 4, here's the deal. It's not a big chapter. So what I did is I recorded a lecture on chapter 4. It will be up there sometime tonight, I think. And you could watch it sometime this week. And it will also be on the exam. So we're not going to lecture live on chapter 4. This will also help us kind of keep on pace so we don't fall too behind with the holiday and everything that's going on. So chapter 4, which will also be on the exam next week, the lecture for that will be up there. I think it's less than an hour. So you just need to kind of watch it and take notes. And again, if you have questions, you could ask during discussion or something like that when we either this week or next week during discussion. So what we're going to do then is we're going to go to chapter 5 now. And we're going to start with that. So give me 1 second to get that all set up here. Okay, click a couple of things here. Okay. Let's do that. Let's do this, maybe. Okay, so we're going to pick up chapter 5, and chapter 5 is not going to be on the exam. So this is starting the new material for exam 2. So this is exam 2 material. Again, as I just mentioned, chapter 4 will be the last chapter that will be on the exam next week. And again, the recorded lecture for that, which I think is like 50-something minutes, will be up sometime tonight. And you could just watch that and take care of it. And again, this will sort of keep us on track. So we're going to bounce around a little bit here in terms of this chapter. So for some of you, I did chapter 5, part of chapter 5 last week during discussion. And for those people that have discussion today, I will do that part of it for you during discussion today. And the part that I did takes care of part of chapter 5 and also the lab that you're doing this week. So that should all kind of be helpful for you. So that's what's on tap for those people that have discussion today. We will take care of part of chapter 5 and the other part that takes care of the lecture or lab part of it that technically is not in a chapter or anything like that. So we'll take care of that for you guys. But right now, we're all start on this chapter here together. So in chapter 5, we talk about a couple different things. We're going to talk about moles, grams, and those type of calculations, which is an important calculation in chemistry. We're going to talk about balancing equations, and we're going to talk about doing calculations from equations, which is known as stoichiometry, which is also an important part of it. All right. So just to make sure everything looks big, it's not really small on the screen. Everything's good, I hope. Yeah. Okay. So we're going to talk about chemical quantities. First thing we're going to talk about is molar mass and Avogadro's number. So the first thing we're going to talk about is what is known as the mole. And the mole is not the furry guy, but it actually does represent something here in chemistry. So many times in life, we have a lot of words that mean something. So when we say that we have a pair of something, that usually implies that we have 2 of something. If we have a dozen, that means you have 12 of something. You know, years ago, they used to call it a gross of pencils, 144. So in chemistry, we have really a name for a certain value, and that is what is known as the mole. And first things first, the mole, this is the actual abbreviation here. They had to make an abbreviation, so they did cut off the E there. So when you see MOL, it does stand for the mole. It does not stand for molecules, and that's a common sort of mistake that sometimes people make. They see MOL and they think molecules, but MO is the abbreviation for moles. And it's basically the amount of elementary substances there are in basically 12 grams of the carbon-12 isotope. And if you remember when we talked about the atomic mass from the periodic table, it was the carbon-12 isotope that was used as the standard to come up with all of those numbers that we see on the periodic table underneath the element, which is our atomic mass. Now, basically 1 mole of something represents 6.022 times 10 to the 23. And as we'll see on the next slide, this is what is known as Avogadro's number. Now, when we talk about it, could be different units, and it can be. So sometimes this may be particles. Sometimes these may be atoms as the units. These units could be molecules, pizzas, you know, shoes, whatever it is. So the number remains the same, and it's always 1 mole, but sometimes we do use different sort of units to go with the number. I would say probably in chemistry, atoms and molecules are the most common sort of units that we use. Sadly, not too much pizza being used there in terms of units, but you know, the atoms and molecules are used. Come back to that picture, I think. So again, most people do round to that 6.022 times 10 to the 23. And like I said, this part of it does change a lot. And mostly it is atoms or it is particles. So what do we use Avogadro's number for? Really, in the most part, we use Avogadro's number as a conversion factor. And it really is our conversion factor to go from typically moles to units of either atoms or molecules. And the way we could use it is like a normal sort of conversion factor. We could make this like a fraction. So we could say that in 1 mole, there is 6.022 times 10 to the 23 atoms or molecules. Or you can put the Avogadro's number up on top, 6.022 times 10 to the 23 atoms over 1 mole. So this is essentially how we use Avogadro's number. Clearly, it's a number in scientific notation. We clearly want to make sure we do use our exponent button, definitely when you're punching it into your calculator. So if you have moles and you want atoms or molecules, you're going to multiply by Avogadro's number. Moles will cancel, gives you atoms or molecules. Or if you're starting with atoms or molecules, you would divide by Avogadro's number. and the atoms would cancel and leave you with moles. So again, usually this is really the only sort of place where we'll kind of use Avogadro's number is sort of to do that conversion. And again, it could either be atoms or molecules, which is your most common one. So sometimes though, people go a little crazy with Avogadro's number. They go, I learned this number, I should just use it in every single calculation I ever do. And you really shouldn't. So again, you should only use Avogadro's number if you're given a number in atoms, molecules, particles, or you're asked to solve for a number in atoms, molecules, or particles. If they really don't mention any of that, you shouldn't use Avogadro's number. And sometimes people use it way too much or try to use it too much, and they end up, again, getting the wrong answer in that case. So as I mentioned before, the term mole represents basically 6.022 times 10 to the 23. And again, you could do that from anybody on the periodic table. So if you say I have 1 mole of sodium, that should have 6.022 times 10 to the 23 atoms of sodium, which you can write 2 conversion factors. If you go, hey, I got 1 mole of iron, that should also mean you have 6.022 times 10 to the 23 atoms of iron. Could also be used for molecules. So if you had 1 mole of water, you would have 6.022 times 10 to the 23 molecules of water. We used not atoms here, but molecules because water is a molecule, as opposed to here we used atoms because we're talking about an atom of an element. If I had 1 mole of CH4, I would also have 6.022 times 10 to the 23 molecules of CH4. So you could apply Avogadro's number to an atom of an element by itself. You could also apply it to any type of molecule. And again, for any one of those that I wrote there on the screen, you could use it as a conversion factor. Again, either Avogadro's number on top to 6.022 to the 23 over 1 mole, or flip it around, 1 mole on top and the 6.022 times 10 to the 23. Any questions on that there? So let's talk a little bit about molar mass. Molar mass is the mass per mole of a substance, so hence the name molar mass. Now, when we talk about molar mass, the units of molar mass are units of grams per mole. So grams per mole are the units of molar mass. And where can we find the molar mass? We can find the molar mass on the periodic table. So on the periodic table is where we can find that molar mass. And the molar mass is found underneath the symbol. It is this number on the bottom. So earlier we called this the atomic mass, and it was, the atomic mass is how many AMU, if you remember. AMU is that atomic mass unit per atom. But through conversions and so forth, basically the atomic mass is the same as the molar mass in grams per mole. What that means is if I wanted the molar mass of hydrogen, it would be that there are 1.008 grams of hydrogen in 1 mole of hydrogen. If I wanted the molar mass of oxygen, there would be 16 grams of oxygen per 1 mole of oxygen. And much like Avogadro's number, we use molar mass really as a conversion factor as well. And molar mass is our conversion to go from grams to moles or moles to grams. And it is a super common conversion, especially this one, going from grams to moles. A lot of stuff that you have to do is that calculation of going from the grams to the moles. So you could do that from the periodic table. Typically, when we pull a number off the periodic table, we typically go to 4 sig figs. So for example, maybe the periodic table you have, for example, the one I might be looking at says underneath hydrogen, 1.007 It's the kind of the number that we see. So typically we do round to 4 significant figures, and that's how we get the 1.008. Just like the one I'm looking at for oxygen, it says 15.99999, a whole bunch of nines. We round it to 16. So we use molar mass really as a conversion factor. And what that means is if you have grams and you want to convert to moles, we're going to divide by the molar mass here. So grams cancel, leaves us with moles. And again, this would be from the periodic table. Or if you have moles and you want grams, you will multiply by the molar mass. Also from the periodic table. Moles will cancel, gives you grams. You could do the molar mass for anybody individually on the periodic table. So if you look at sulfur, 32.07 grams of sulfur gives you 1 mole of sulfur. And again, you could write 32.07 grams per mole, which would be the molar mass. Or if you need the mole on top, you could do the 32.07 grams on the bottom as a conversion factor. You could do it for, again, individual elements. If you looked at nitrogen, there is 14.01 grams in every mole of nitrogen. And that basically means that the molar mass of nitrogen is 14.01 grams per mole. And you again could use it as a conversion factor, 14.01 grams of nitrogen over a mole of nitrogen, or a mole of nitrogen is 14.01 grams. You could also do it for molecules as well. So for example, H2O, you basically go to the periodic table and you add up all the parts. So there are 2 hydrogens, each at 1.008 grams per mole, plus 1 oxygen at 16 grams per mole, which means the molar mass of water would be 18.02 grams per mole. When you calculate the molar mass, the number always stays with the grams part, and it's always 1 mole. So the bottom is always 1 mole, or wherever the mole is always 1 mole, and the grams always stays with the number. So for example, if I had C2H4, there are 2 carbons. If you go to periodic table, carbon is 12.01 grams per mole. Again, that is the number on the bottom of C on the periodic table, plus 4 times 1.008 grams per mole, which again is the molar mass of hydrogen on the periodic table. And if we add all that together, we would end up with 2 times 12.01 plus 4 times 1.008 gives us 2805 grams per mole would be the molar mass here of C2H4. Question on that there. Molar mass is an incredibly common conversion that you need to use. And again, basically from the periodic tables where you get that, you add up all the parts essentially. So that brings us back to that picture I kind of went by real quick. Let's go back to that right here. So when we look at these pictures, these are all represents 1 mole of all these substances. And you may say, if they're all 1 mole, how come it looks like there's kind of different amounts of stuff in here? And that's because, for example, 1 mole of sulfur, if you look on the periodic table, represents 32.07 grams, while 1 mole of iron represents 55.85 grams. 1 mole of sodium chloride would be represented by sodium, which is 2299 grams per mole, and chlorine, which is 3545 grams per mole. So the molar mass of that is 58 something there, 44 I think. 5844 grams per mole. So what this shows you is, although they're all 1 mole of each of these things, when we say we have a mole of sulfur, that represents 32 grams of it. When we have a mole of iron, it represents 55. and change, sodium chloride 5844. So although they all do represent 1 mole of each of these guys, 1 mole represents a different quantity in terms of mass for each of these guys. Any questions on that? Okay. And here again is a picture, kind of what we just went through. So anybody from the periodic table, you can basically pull off the information from the periodic table, and it is that it is that one that's underneath the symbol. Is that the slide you're looking for? Yes. No. Okay. So any element, you can pull it off. And again, the number represents how many grams there are per mole. And again, round to 4 significant figures. And usually if you're asked to give the molar mass of a substance, 4 significant figures is typically the common one that you go with. And if it's some type of molecule or something like that, you pretty much just add up all the parts. And then that's how many grams there would be per mole. All right, so let's see. Let's take a look at some here and what we could do on some calculations involving these guys. We oftentimes will use these in calculations, like I said, pretty much as conversion factors, with your molar mass being your conversion factor, grams to moles or moles to grams. And again, your Avogadro's number in those cases where something about atoms is involved or molecules, that's when you want to use it. Again, you don't really want to use it in any situation because usually people will sometimes use it where they divide by Avogadro's number, then multiply by Avogadro's number, so at least they cancel each other out and they might get the right answer. But again, if there's no mention about molecules, atoms, anything like that, don't use Avogadro's number. If you see something with those units in it, either a number given to you or a number you need to find, you probably need to use Avogadro's number. All right, so I think we might have some examples here, I think. Yep. So why don't you try these 2 examples? First off, how many moles of helium are there in 5.46 grams of helium? And how many grams of zinc are there? In case you don't have a periodic table, I'll give you what these look like. So helium, if you look on the periodic table, we'll say 4.003 underneath it. And zinc, we'll say 6539. All right, so see what you come up with. So looking for how many moles in the first one, how many grams in the second one, and see what you get. So that's a good question. So let's talk about these guys here and see what we should use and what we maybe should not use. So let's take a look at the first one here. We are looking for how many moles of helium are there in 5.46 grams. So I see grams mentioned, I see moles mentioned. I do not see anything mentioned about atoms, nothing mentioned about molecules. So that means that we do not need to use Avogadro's number here. Again, you only need to use Avogadro's number if there's anything that involves atoms or molecules either given to you or you're looking to find it. So really what we're doing here is a conversion between grams to moles. And really what that conversion factor that we use is the molar mass. And again, we get the molar mass from the periodic table right there. And basically what that means is that the molar mass of helium is 4.003 grams per mole, which we could use like this. We could also use it in the opposite direction if we needed to. We could put the moles on top and 4.003 grams on the bottom. Most people will say the molar mass is 4.003 grams per mole. But again, you could think of it as a conversion factor. So since we don't need Avogadro's number, what we want to do is start with the 5.46 grams of helium. And just like when we were doing conversions, the best way to think about it is just to get rid of the units. So I have grams on top, which means in order for it to get rid of the units, I actually need to use the conversion on the right here, where I have the grams on the bottom. So essentially I'm dividing by the molar mass here. And again, that comes from the periodic table right here. This guy comes from the periodic table. Grams are going to cancel out. And I think as I saw in the chat box there, the answer is 5.46 divided by 4.003 by punching in right. And we will get 1.36 moles of helium as our answer. So again, here, nothing mentioned about atoms or molecules, so we don't need to use Avogadro's number. And this is what I was saying earlier. Sometimes people go, I know that number, I'm just going to try to use it everywhere, but you don't need to use it everywhere. In terms of sig figs, really you could consider this a conversion factor. So really the significant figures is based off of this guy, and that's 3 significant figures. So probably want to end up with 3 significant figures when it's done. Questions on that first one there? Okay, so let's take a look at the second one. We are looking for grams and we are trying to find moles. So I'm sorry, we're looking for grams and we're given moles. Remember, MOL is the abbreviation for moles, not molecules. Again, no mention of atoms, molecules, or anything like that. So again, our conversion factor to do that is going to be the molar mass from the periodic table. Again, that is this number here, which essentially means that there's 65.39 grams per mole of zinc. Or again, if you want to use it as a conversion factor, moles of zinc on top as well, and the 6539 grams on the bottom. So here again, we're just going to kind of use a conversion type factor, and we're going to go 0.256 moles of zinc. Again, going opposites to get rid of the unit we want. So we do need to use the one here on the left as the moles are on the bottom. So we will get the moles of zinc is 65.39 grams. The moles will cancel. We're essentially taking 0.256 times 65.39, and it looks like 16.7 moles of zinc. And again, 3 sig figs based off of that original number, which has 3 significant figures. Question on those two. So sometimes it's best to kind of think of these things sort of like a conversion problem where you want to get rid of the units you don't want to keep and get to the units that you want to keep. Thank you. It is grams. Thank you very much. It's a good thing there's an eraser. All right. Thank you. The number's right, at least. There we go. So I guess we are left with grams, which would make sense based on what was asked. Thank you very much. All right. Let's take a look at another one here. Why don't you give it a try? What is the mass in grams of one gold atom? So you got one individual gold atom. What is the mass of it in grams? And from the periodic table, that's the number for gold. Okay, let's take a look and see how we're doing. So in this case, obviously, if the second part here wasn't given to you, what is the mass in grams of one gold atom? So the key word here is atom. So we do know that we need to use Avogadro's number in this case, because in this particular case, we're given atoms. So the idea here is we have atoms. We eventually want to get to grams. So we could use Avogadro's number to get us to moles. And then we could use the molar mass from the periodic table to get us from moles to grams. So that's the first thing we want to do is we want to start with one gold atom. And we want to use Avogadro's number to get rid of atoms. So we want the atoms on the bottom. So that means that there would be 6.022 times 10 to the 23 atoms of gold in a mole of gold. If I stop right there, the atoms of gold would cancel out. And if you wanted to, you could get an answer at this point, or you could continue on with the calculation. And what we can do is I'm going to continue on. From the periodic table, we see that the molar mass of gold is 197 grams per mole. Or again, we could use it in the opposite direction if we needed to. So in this particular case, if we stop right now, we would be in units of moles, which are on top. So to cancel it out, we do need to use the molar mass in grams per mole. And that would give us 197 grams of gold per mole. Moles of gold would cancel in this particular case. So what we're going to do is multiply across the top. So that is basically 1 times 197, hit equals, then divided by 6.022 exponent button 23. And if you punch all that in correctly and your calculator doesn't die like mine, let's see, you will get a number. I think what we got going on in that box there should be 3.271 times 10 to the minus 22 grams of gold. That is a super small number, and we're talking about, in theory, one individual gold atom. Again, you could get an answer in between here and continue on with the calculation. Try not to round too much, and you should be okay. If you were wondering about significant figures, I went with 4 significant figures here because technically speaking, one gold atom would be an exact number. You would technically count one gold atom, which means you could technically go with any sig figs you like in terms of numbers. I went with 4 since the molar mass was 4 significant figures and stuff like that. Question on that calculation. A reminder again, when you're using Avogadro's number, make sure you use that exponent button on your calculator. You don't have to hit the multiplication button, shift log, anything weird like that. Just make sure you use that EE button or you will find yourself off. Any questions on that calculation there? Why don't we try a couple more just to make sure? So let's go with, why don't you do, let's see here. How many grams are in, let's go with 32.5 grams of, we'll do NH3. Let's see. How many molecules are there in 12.5 grams of, let's go with C2H5O. I'll give you some numbers from the periodic table that might help in case you don't have it. Nitrogen is 1401 grams per mole. Oxygen is 16 grams per mole. Hydrogen is 1.008 grams per mole. So take a couple minutes and figure those two out. Looking for how many grams in that many grams. That's not good. How many grams are in that many? Let's not do grams to grams. There's no calculation there, right? Let's go with moles. That would probably be better, I suppose, right? It's a quick calculation. It's just quick. For the molar mass for hydrogen it's 1.008, if that's what you're asking. This number. It's from the periodic table, same numbers you should see up there. Okay, let's take a look and see how we're doing since we're getting to the end here. So taking a look at the first one here that I fixed the bad problem I wrote originally. I'll get rid of that even more. So we're looking for how many grams there are in 32.5 moles of NH3. So again here, there is no mention of atoms, no mention of molecules. So we do not need to use Avogadro's number. This is just a straightforward grams to moles conversion. And that is the molar mass from the periodic table is what we use to do that. In order to do that, we essentially just need to add up all the parts for NH3 from the periodic table. So if we go to the periodic table, nitrogen is 14.01 grams per mole. That's for the nitrogen. We're going to add it to 3 times the molar mass of hydrogen from the periodic table, which is 1.008. And if we do that, that will get us 17 and some change there. 1703 grams per mole would be the molar mass here for our NH3. Any questions on that so far? Remember, we're really just going to kind of use the molar mass as a conversion factor. So in this particular case, we are starting with moles. So 32.5 moles of NH3. So thinking about it in a conversion factor sense, we have moles on top. So we want the moles to cancel. So moles has to go on the bottom. So in this case, the moles will go on the bottom. And it's 17.03 grams of NH3 on top. The moles will cancel. And we will end up with, looks like, about 554 grams of NH3. Any questions on that calculation? So when we look at this, a couple of things sometimes people do with the molar mass, especially when we get into balancing equations or something like that. When you do the molar mass, it is always per 1 mole. So it's always 1 mole, and the grams always has the number that goes with it. Even if you have an equation where there's a number in front of it, like 2NH3, if you're asked to calculate the molar mass for NH3, it is always based on just the formula. So you should always take the formula. Again, later on in this chapter, obviously, we'll see balanced equations. There'll be some numbers in front of it. And you always want to do it based on formula. I personally rounded to 554 because I had got on my calculator when I punched it in 553.605. And that's because I didn't really round the 1703. So I just took the 1703.4 and times it by 32.5. If you rounded the molar mass, which I did on my calculator, that's how I got here. If you rounded to 1703, you get 553.4, which should be 553 like you punched in there. So that's okay. It just happened I didn't round the molar mass on my calculator and just continued on. So either one is sufficient. If you did round, you will get the 553. If you didn't kind of cut off that last number for the molar mass, that's how I got up to 554 in that case. Other questions on that? So again, basically, yeah, I would take both, to be honest with you. Probably the right answer should be probably the 553 because you probably should round this to 4. Happens sometimes. Sometimes it doesn't make a big difference. You guys kind of continue on with it, but that's what happened in that case. I just continued on with when I did the molar mass 17.034 and multiplied it. So the correct answer, probably the 553 is truly the real correct answer, but they both would have been okay in this case. All right, last one here. How many molecules of are there in 12.5 grams of C2H5O? So molecules is our keyword here. That means I need to use Avogadro's number here. That's going to take me to moles, and from moles, I'm going to need to get to moles. So I got to go grams to moles, and then to Avogadro's number going in this direction. So the first thing we need is the molar mass, because we do need to go grams to moles, because Avogadro's number is how many moles there are per molecule. So to get that, that would be 2 times 12.01 grams per mole for the carbon from the periodic table, plus 5 times 1.008 grams per mole for our hydrogen, and 16 grams per mole from the periodic table for our oxygen. And if we put all that together, 2 times 12.01 plus 5 times 1.008 plus 16 gets us 4506 as the molar mass. So that is the first part we're going to do. We're going to take those grams and use the molar mass from the periodic table to convert our grams into moles. So that would be 45.06 grams per mole. Grams are going to cancel. Again, you can get an answer at this point, but I'm going to continue on. And this is where we're going to use Avogadro's number to go from moles on the bottom to molecules on top. And here it would be molecules because what we're talking about there is a molecule. So the moles will cancel out. So mathematically, what we're doing is we're taking 12.5, we're multiplying by 6.022 with our exponent button to the 23. I would hit equals, divide it by 4506, going to give us here 1.67 times 10 to the 23 molecules of C2H5O. Again, 3 sig figs based off of this number here. You can, again, get an answer here and continue on. Again, just watch the rounding, but you should get something very similar. Question on those. Grams to moles, moles to grams, any of those things? Okay, so we will stop there for today. So we're into chapter 5. Those that have discussion today, we will talk about what I talked about with everybody last week in discussion on Wednesday. That way you'll be good to go for the lab this week as well. And again, a reminder, the exam will be 1 week from Wednesday, covers chapters 1 through 4. And later tonight, chapter 4's lecture will be posted up on Canvas that you can watch it again. I think it's under an hour, so you can watch that and catch up with that. It will be. So the exam will be a week from Wednesday. It will open up at the start of lecture around 5:30. You'll have the entire lecture time. I may even let it open maybe just a little bit earlier. That way you might not feel so rushed if you have lab or something like that. But you will get to. You get, are you talking about chapter 4's lecture? I think it's only like 55 minutes, maybe the video, something like that. If you're having trouble with exponents, it's probably the way you're punching it in. You want to make sure you use your exponent button. That should be the EE button on your calculator there. So make sure you are using your EE button when you punch in Avogadro's number. That would be my guess. All right. Other than that, if you didn't put here for a roll, make sure you do that. The answer to the last one is 1.67 times 10 to the 23. Yeah. Molecules. And I'll see those that have discussion in a few minutes. And those that have lab, have a good rest of your night. And I'll see you on Wednesday. And those for discussion, I'll see you in a few. Bye-bye. Have a good one.